Welcome back to the fourth video for the chapter Coordination Compound. This is the continuation of the last three videos for the chapter Coordination Compound. So in the last video I left you with the topic of isomerism, where we came to know about different types of isomerism like linkage, coordination, ionization, solvate, geometrical, and at the same time optical isomers. So today in this video we are going to learn about the bondings in coordination compound. What are bondings in coordination compound? Means how they form bonds in coordination compound. So here this was firstly given by the valence bond theory. Many approaches were made where there were crystal field theory, valence bond theory, molecular orbital theory, ligand field theory. Many theories were there. But here first of all we are going to consider valence bond theory. Now what is valence bond theory? This valence bond theory, it has two postulates. According to this, the first postulate is that the metal atom, we will consider only the metal atom. The metal atom or ion under the influence of ligand, it uses its n-1d orbital or s or p or ns and np and d orbitals for hybridization. So once again we have to go back to class 11 and we have to learn about hybridization here. If you remember, we have already learned that in case of hybridization in our organic compounds, we are only limited with the s and the p orbital. But now here in case of metals, our d orbital will also come into the picture. And these orbitals, they hybrid and yield a set of equivalent orbitals of definite geometry to such as octahedral, tetrahedral and square planar. Another one is that these hybridized orbitals are allowed to overlap with the ligand orbitals that can donate electron pairs for bonding. So now this whatever the bonding is happening here, this bonding occurs which is based on this spectrochemical series. So about this spectrochemical series, the spectrochemical series is nothing, it is just the arrangement of the ligands or arrangement of the ions which is arranged in basis of increasing field strength. Now what is about this field strength, you will know when we will start this topic here, when we will start this part, like what is valence bond theory and how based on this what is the application of valence bond theory. You will come to know about this spectrochemical space, but at the moment you just keep in your mind now that this is the arrangement of the ligands on basis of their field strength, and this is the increasing order. Means this is how they are in order arranged in the increasing order, where iodine is the least one and carbonyl is the highest one. Now here this water ligand, this is the separation between the weak ligands and strong field ligands. Up to oxygen you will have weak field ligand, and after this one you will have your strong field ligand. Means up to water you have your weak field ligands, and prior to that you will have your strong field ligands. So now we know about the hybridization. So these are the different types of hybridization. Like if the hybridization is sp, the geometry is linear. Then if sp2, then trigonal. Sp3, then tetrahedral. dsp2, then square. dsp3, then this one. d2sp3, then d3sp3. So this is how we have arranged it here. Now you can see one thing, that if you have sp3d2, then also you have octahedral, and if you have d2sp3, then also you will have octahedral. So now we will come to know that how this hybridization everything comes, means how this sp comes and how this sp3 sp2 will come to know in this video today. So now using this valence bond theory, we can predict the shape and structure of different coordination compounds. Now I'll show you that how to predict the shape and structure for a compound. Also you can tell about the magnetic property, that whether it is diamagnetic or whether it is paramagnetic using this valence bond theory. Now how it is done, for that let me take an example of cobalt, and this is suppose hexaimine 6, and this carries a charge of +3. So now first step is here that you have to find out the oxidation state of your metal. Now in my case my metal is cobalt. So if I am going to determine the oxidation state of my metal, you all know how to determine the oxidation state here. So if I am going to determine the oxidation state, cobalt will be X plus amine is 0, and this is having a charge of 3, so this will have equal to 3. So my oxidation state of cobalt is 3 here. That is the oxidation state of my cobalt. It is 3 in the given compound. So now the compound which I have taken, it was cobalt NH3 whole 6, and then it had a charge of 3 positive, and I got that my cobalt has a charge of 3 positive, means the oxidation state is 3 positive. So now we have to write the electronic configuration for cobalt, which is in the 3 positive state. So I'll just write for the ground state first. So now cobalt, the ground state, it is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now if you remember that cobalt, it comes in number: scandium, titanium, vanadium, chromium, manganese, iron, cobalt. It is number 27, so it will be 3d7. So now here your cobalt is in 3 positive state. So when it is 3 positive state, it means that 3 electrons are less than the usual one. Now if you remember what I said that in your previous class, that firstly the electron will go from the s orbital and then from the d orbital. So cobalt in the 3 positive state will have 3 electrons less. That will be 1s2, 2s2, 2p6, 3s2, 3p6 and 3d6. Here 2 electrons will go from this orbital and 1 electron will go from this orbital, so it will become 3d6. So now the 3d6 orbital, the 6 electrons, let me draw this one. Now 6 electrons, these are the, suppose the d orbitals, 1, 2, 3, 4 and another one, 5. This is my 3d orbital, and now in my 3d orbital how many electrons are there? In total 6. So follow the Hund's rule: 1, 2, 3, 4, 5. First of all are singly occupied and then the pairing occurs. So this is my 3d6. Now we have to see that whether my ligand, whatever the ligand is used, it is a weak field ligand or strong field ligand. Now comes the use of this. One. Now from here we have to see that whether my ammonia, means NH3, it is a strong field ligand or it is weak field ligand. So if you pay your attention here in the chart here, this ammonia is present here. It means that it is a strong field ligand, means after water you have it here, so it is a strong field ligand. So when you have your strong field ligand, then in that case whatever your electrons are present in the d orbital, they start pairing. It means that when this ligand will approach the metal, what will happen? Like this is the 3d cobalt 3 positive state, cobalt 3 positive state. This is the electronic configuration. And now when you have your ligands approaching, when this cobalt will approach, when this ammonia will approach this cobalt, what will happen? That electrons which are present in the d orbital, they will start pairing. So now if this is my d orbital, 1, 2, 3 and this is another one, 5. Now my M is approaching, so the electrons will start pairing. So it is already paired. Now this is one, this is another, this is one and this is another. All the 6 are paired. Now you have to see that how many ammonias are there, how many amines are there. So 6 ammonia are there. So for that you need 6 vacant orbitals. Now you have only 2 vacant orbitals which are from your d. These are your 3d orbitals. So now you have only 2. Now you need 4 more. So let us bring after d, you have your 4s orbital. So now this 4s, it has only 1. Now your thirst for orbital is not yet quenched, means you require 6 and you have got only 3. So after that it will come your 4d orbitals. Now these 4p orbitals, these 4p orbitals will come, and these 4p orbitals, they have 3 suborbitals. These are the 3 suborbitals. So now one ammonia will bond here, NH3, another will go here, this will be your NH3, another will be here, your NH3, and NH3 another here, then again NH3 here, and then again NH3 here. So in total, these are the orbitals that you are using. You see, these are the orbitals that you are using. So how many d orbitals you have used? How many d orbitals you have used? You have used 2 d orbitals. How many s? Only one s. And how many p orbitals you are using? So you are using 3 p orbitals. So your type of hybridization is D2sp3 hybridization. So now when the hybridization is D2sp3, you can see it in your book. If your hybridization is D2sp3, the shape is, if your hybridization is D2sp3, the shape is octahedral. The shape is octahedral. And now another thing is your magnetic property. So now for the magnetic property, you see, magnetic property. Now if you pay your attention here, you see all the electrons which are present in the orbital, all the electrons present in the orbital, all of them are paired. So when all the electrons are paired, your magnetic property is diamagnetic. It is diamagnetic. So this is how we have to determine the shape for different molecules or different coordination compounds given in this way. Now I'll be doing another one where no pairing will occur. Here it was a strong field ligand. Now another one I'll do it using a weak field ligand. Suppose let us take another example. Now let us take an example of fluorine. Suppose let me do another question for you all. So let us take another question, and that another question will be, suppose cobalt and 6 fluorine, and then suppose this is a charge of 3 negative. So now here we have to calculate the, first of all we need to calculate the oxidation state of my metal. So I am calculating it. X plus fluorine has a charge of 6, which will be -1 is equal to -3. So from here, if I am going to calculate for X, I'll get it as 3. So now here once again my cobalt has an oxidation state of +3. Now cobalt +3. So first of all, cobalt 1s2, 2s2, 2p6, then 3s2, 3p6, then 4s2 and 3d7. Now once again, X is in 3 plus 3 state. It means that you will have 3 electrons less. So it will be 1s2, 2s2, 2p6, 3s2, 3p6, and you will have your 3d6, because 2 electrons from here and 1 electrons from here are less. Now once again, the arrangement of the d orbital, the electrons present in the d orbital, let us do it. Now my d orbital 3d6. Now we don't need to consider all of these orbitals. We have to only consider the d orbitals. Now here d orbitals. Now this is my d orbital, 1, 2, 3, 4, 5. Now following the Hund's rule again, fill the electrons, 3, 4, 5, then and 1 here. Now 6 are done. Now the next step is that we have to see that whether my ligand is a weak field ligand or a strong field ligand. Now once again, let us move to the previous slide. Let us move to the previous slide and let's see here. Now here you see my ligand was, this time I have used the ligand fluorine. Now you see fluorine is present here. Now if fluorine is present here, it means that it is a weak field ligand. Now in case of weak field ligand, your pairing will not occur. Now when your pairing is not occurring, it means that the orbitals will remain as they are here. So now in this case, you have how many ligands approaching? You have 6 ligands. It means that you need 6 vacant orbitals. Now from where the 6 vacant orbitals will come? Then after the 3d orbital, you have your 4s orbitals. So draw the 4s orbitals. This is your 4s. 1 is done, but you need 5 more. So again after 4s, you will have your 4p. Then in 4p you have your 3 suborbitals. Then 1, 2, 3, 4 are done. You need 2 more. Then that 2 more will come from your 4d orbital again. D orbital, so it will have your 5 suborbitals. 5 suborbitals, but you want only 2. It means that you need the orbitals from here up to here. Up to here. So now you see the arrangement of the orbitals. First of all, you are using s orbital, then you are using 3 p orbitals, and then you are using 2 d orbitals. Now once again, this is your hybridization. So your type of hybridization, it is your sp3d2, and when your type of hybridization is sp3d2, the shape once again it is octahedral. The shape once again it is octahedral. And here now the next is your magnetic property. Next comes your magnetic property. Now the next thing is that you need to see the electrons, how they are present. So now in the d orbital, you see the electrons are unpaired. So when the electrons are unpaired, the given compound is paramagnetic in nature. They are paramagnetic in nature. Now paramagnetic compounds, they repel the magnetic fields. These are the paramagnetic complexes. So depending upon the ligand, we can predict the magnetic behavior, we can see the type of hybridization, we can see the shape of the orbital. One more thing is here, whether a compound is outer orbital complex or inner orbital complex. That is how you are going to determine. Like in the first case, here, what was my type of hybridization? So my type of hybridization was d2sp3. It means that my d orbital is present inwards. So when this d orbital is present inside, that is known as inner orbital complex. That is inner orbital complex. And in the next case, here if you see, my d orbital is present in the outer portion. So when my d orbital is present in the outer portion, that is known as outer orbital complex. Okay, so this is inner orbital, and inner orbital complexes are also known as low spin complexes, and outer orbital complexes are known as high spin complexes. They are known as high spin complexes. So I'll be doing one for you, and you have to see the presentation, how they are presented well. See, suppose let me take an example of nickel cyanide. Suppose NiCN and then 4, and this is 2 negative. First step, determine the oxidation state. X plus 4 times minus 1 is equal to minus 2. Then from here you will get x is equal to 2. So now when your x is 2, now I'll be writing directly the oxidation state and directly the Ni2 positive electronic configuration. Now in this case you have your 3d, means in the 3d orbital you have 8 electrons. In the 3d orbital you will have your 8 electrons, because nickel, copper, zinc, it is in the 28th number and 2 positive are there. So 2 electrons will go from your 4s orbital. So if you write the electronic configuration of nickel and then nickel 2 positive, you will get how this became 3d8. So now next we have to go for the d orbital. Draw the d orbital. So now this is your d orbital. These are your 5d orbitals. Start writing the electrons following the hand rule. 2, 3, 4, 5. Then the pairing will occur 6, 7, 8. So now 3d8 here. Now this is your 3d8 orbitals. Now next thing is that you need to see that whether your cyanide is a strong field ligand or a weak field ligand. So actually nickel is a strong field ligand. So now when nickel is a strong field ligand, then the pairing of electron will occur. Then you will write a line here that since cyanide is a strong field ligand. So the pairing of electrons occurs in the d orbital. And if it is a weak field ligand, then you will write that since suppose X is a weak field ligand, so the pairing of electron does not occur. In that case, you will not mention your orbital. Now here cyanide is a strong field ligand, so the pairing of electron occurs in the d orbital. So now you will just pair the electrons. Now first this is paired, this is also paired, this is also paired, and these two were unpaired, so they will come here and they will get paired. So now you have to see that how many cyanides are with you. You have 4 cyanides, you have here only 1 orbital, and that is your d orbital. This is your d orbital. You need 3 more orbitals, so next will come your 4s orbital. तो ये आ गए तुम्हारे 4s ऑर्बिटल. अब एक ही आया लेकिन हमें और 2 चाहिए, तो लेकर आओ p को. p में कितने होते हैं? इन योर p यू हैव योर 3, तो 3 हो गए. तो यहाँ से ये हमें तो चाहिए 4, तो एक ले लो s, एक ले लो d वाला, टेक 1 d, टेक 1 s and take 2 p orbitals. So now how you will write? You will write below this, you will write type of hybridization. Type of hybridization, you will write it as dsp2. Then after that you will write shape. अब shape अगर जानना है तो shape तुम्हें book में मिल जाएगा. तुम्हें it is there in your book. Now if the hybridization is your dsp2, if your hybridization is dsp2, तो shape होता है उसका square planar. अब shape हो गया square planar. अब type of hybridization हो गया, shape हो गया. अब उसके बाद में लाना है कि इसका मैग्नेटिक बिहेवियर क्या है. तो अब मैग्नेटिक बिहेवियर में देखो, जस्ट सी ऑल द इलेक्ट्रॉन्स आर पेयर्ड. सो व्हेन ऑल द इलेक्ट्रॉन्स आर पेयर्ड, तो इसका जवाब होगा डाया मैग्नेटिक. जब सारे के सारे पेयर्ड होते हैं तो ये कंपाउंड होता है तुम्हारा डायमैग्नेटिक. अब टाइप ऑफ हाइब्रिडाइजेशन लिख दिया, शेप लिख दिया, मैग्नेटिक लिख दिया. अब उसके बाद लिखना है टाइप ऑफ कॉम्प्लेक्स. अब लिखेंगे हम टाइप ऑफ कॉम्प्लेक्स. अब टाइप ऑफ कॉम्प्लेक्स में हमें लिखना है कि ये इनर स्फीयर है या आउटर स्फीयर है. तो यहाँ देखो डी कहाँ है, अंदर की तरफ है, तो ये हो जाएगा इनर स्फीयर, इनर स्फीयर कॉम्प्लेक्स. तो हमने टाइप लिख दिया, शेप लिख दिया, मैग्नेटिक बिहेवियर लिख दिया, टाइप ऑफ कॉम्प्लेक्स लिख दिया. एंड दीज आर द 4 थिंग्स दैट यू हैव टू मेंशन फॉर एवरी क्वेश्चन. So I'll be giving you some practice problems along with this video, so I hope that you will be doing it. So now we'll just end it up to here. Thank you for watching the video. Thank you for your attention. We'll meet with the next video in the next class. Thank you for watching. Thank you very much.